In this lesson, we will examine how the first and second derivatives affect the shape of a graph. We will start this section with the mean value theorem, which gives us a basic explanation of how functions behave. Right? So the mean value theorem says if f is a differentiable function on the interval a to b, in a closed interval, so that means we can take the derivative and evaluate it at any value between a and b, including a and b, then there exists at least one number c, it could be more than one, between a and b such that f prime evaluated at c is equal to f of b minus f of a over b minus a. So in other words, the slope of the tangent line at some point is equal to the slope of the line connecting the points A and B on the graph, or the secant line. Right? In other words, we can cross multiply this and also get f of b minus f of a is equal to f prime of c multiplied by b minus a, and that it kind of gives us an equation of a tangent line y2 minus y1 equals to the slope times x2 minus x1. So let's take a little bit of a closer look at this. So if I have a function and I take an interval from a to b, find the points f of a and f of b on my graph, and connect them, I get a secant line, and somewhere on that graph I'm going to have a point where if I draw a tangent it would be parallel to this line. So the slope of that line gives me the average rate of growth, and the slope of the tangent line gives me the instantaneous rate. So at some point the instantaneous rate is going to equal to the average rate. In this case, that's where point C would be. I have a tangent that's parallel to the secant I had drawn. And there is another one here. The theorem guarantees there is at least one. There could be more. So there I have a point D where the tangent is also parallel. If I kind of bring this to something we're more familiar with, so if the average rate, so let's say that's my average speed over a 50-mile trip. So let's say my average speed was 60 miles per hour. This theorem guarantees that at some point during that trip, I was going actually 60 miles. I wasn't going 60 miles throughout, so I could have been going slower at some point, faster at some point, but at least at one point during that trip, I was going 60 miles per hour. The mean value theorem reaffirms some of the things that we had observed about the derivatives and behavior of a function in previous sections. Right, so it gives us what we had seen as an increasing and decreasing test. That if the derivative of a function is positive on an interval, then the function is increasing on that interval. So as long as the function is always positive on the interval, then the function is increasing. And if the derivative is negative on an interval, then the function is decreasing on that interval. Right, so let's take a look at an example. Here we are given a function 4x cubed e to the x, and we are asked to find out where this function is increasing and where it is decreasing. Well, as we just observed, first thing we need to do is take the derivative of this, find out when it is positive, when it is negative, which means we got to start by finding when it is equal to 0. And then based on that, we can decide if it's increasing or decreasing. So this is a product, 4x cubed times e to the x. To take the derivative, we need to use the product rule. So we'll start with that. The product rule says I got to take a derivative of the first part. So derivative of 4x cubed is 12x squared, multiplied by the second part of that product, e to the x, plus the derivative of the second part, so derivative of e to the x, which remains e to the x, multiplied by the first part of the product, which was 4x cubed. clean this up a little bit, just reordering things. I get 4x cubed e to the x plus 12x squared e to the x. Now, we need to find out when this is 0 in order to find out when it is positive or negative. So we'll start by factoring this. I can take out a 4x squared e to the x out of both terms. And now I have a multiplication of 3 pieces, 4x squared times e to the x times x plus 3. We want to know when this is equal to 0. So we'll set each part of that product equal to 0. So 4x squared is equal to 0. I get x is equal to 0. If e to the x is equal to 0, I have no solution. E to the x cannot equal 0. E is a positive number. Taking it to an exponent would not give me 0. And when x plus 3 is equal to 0, subtracting the 3 gives me x equals negative 3. So these numbers, I have my two solutions, x equals 0 and x equals negative 3. Divide my number line into 3 intervals, right? So we get a part where x is less than negative 3. We have a part that's between negative 3 and 0, and finally a part that is bigger than 0. And we're going to go back and check what happens to the first derivative in each of these sections. So starting with numbers smaller than negative 3. An easiest place to check the derivative's sign is in the factored form, right? So if I have x is smaller than negative 3, let's say negative 4, the 4x squared is always going to be positive regardless of what I plug in, because x is squared. And multiplying it by 4 doesn't change its sign. So this part is always positive. E to any number is also always positive, whether the number is smaller than negative 3 or bigger than negative 3, doesn't matter. So these two quantities are going to be positive. Now, if I plug a number smaller than negative 3 into this part, negative 4, negative 5, negative 5.93, no matter what number I plug in, this part is going to end up being negative. So we had a positive quantity multiplied by a positive quantity multiplied by a negative quantity. That means our derivative is going to be negative. And that means my function is going to be decreasing on that interval from negative infinity to negative 3. And we'll repeat this for the other two intervals between negative 3 and the 0. If I plug any number between negative 3 and 0 back into my factored form of the derivative, I still have a positive quantity here, positive quantity there, and any number between negative 3 and 0, if I add a 3 to it, I'm going to get a positive amount. So I have a positive quantity times a positive quantity times a positive quantity. The entire product is going to be positive. And as a result, my function is going to be increasing on that interval from negative 3 to 0. And finally, in the last interval, when x is bigger than 0, if I follow the same process, 4x squared, no matter what number I plug into it, positive. E to the x is always positive. And a number bigger than 0 added to 3 is also going to be positive. So my first derivative is positive, which means my function is still increasing from 0 to infinity. Right, so now I know where the function is increasing and decreasing. If I look at a graph, it should kind of confirm whether this is true. So this is what the graph of 4x cubed e to the x looks like. Notice the graph is decreasing all the way to negative 3 when x is negative 3. And then it starts increasing, and then it increases straight through 0 and continues increasing. Next, we're going to see what all of this tells us about the maximum minimum of the function. So the first derivative test is what we're going to use to decide on the max and min. The first derivative test says, suppose that c is a critical number for a continuous function f. Then, if our first derivative changes from positive to negative at c, then a function has a local maximum at c. And if the first derivative changes from negative to positive, then it has a local minimum. And finally, if it does not change a sign, then it has no local max or min at c. right? So it should kind of make sense if my function was increasing and then goes to decreasing, then it has a local max. If it was decreasing to start with, then it all of a sudden starts increasing at C, then C has to be the lowest point. And if there was no change, if it was increasing and it continues to increasing, then the function has no local maximum or minimum. So in the past, we had learned that the critical values could potentially tell us if it's a minimum or a maximum. And this kind of tells me under what conditions the critical numbers are actually maximum or minimum. So if I go back and look at the example we just looked at, we had the derivative change from a negative to a positive at -3. So that makes -3 a local minimum. So we were decreasing and then started increasing. While at 0, my function went from positive and it remained positive. That means the function was increasing and continues increasing. Therefore, 0 was not a maximum or minimum. In this case, 0 is what we call an inflection point. And that brings us to the next subject that we're going to look at, and that has to do with concavity, right? So we'll start by formally defining the concavity of a graph. A graph is said to be concave upward if the slope of the tangent line increases from left to right. So if I am looking at this graph, notice if I draw a tangent line, the slope here is negative, then it kind of becomes 0, and then it becomes positive. So the slope is increasing from left to right. So I keep getting larger and larger slopes that go from left to right. We call this shape concave upward. And the flip side of that, a graph is said to be concave downward if the slope of a tangent line decreases from left to right. So literally, if I flip this, I'm going to get slopes that keep getting smaller and smaller as I go from left to right. Okay, and notice that the changes in that slope are dictated by the derivative of the slope. And the derivative of a slope is really the derivative of the derivative, or the double prime of the function we started with. So next thing we do is formalize the relationship between the second derivative and the graph of the function. The concavity test tells us that if the second derivative of a function is positive on an interval, then the function's concave upward on that interval, right? Because the second derivative is the derivative of the slope. And if the derivative of the slope is positive, it means the slope is increasing. Therefore, my function is going to be concave upward based on the definition of what it means to be concave upward. And the same is true, or the opposite of that, I guess, is true. If the second derivative is negative on an interval, then the function is concave downward because the derivative of the slope is negative. It means the slope is decreasing. And finally, we're going to kind of connect all of this together, and we're going to look at the second derivative test. And the second derivative test says if my second derivative is continuous near a number c, right? So I'm only worried about that number c as long as the second derivative is continuous near it. Then if my first derivative was 0, which means I had a critical number, and the second derivative is positive, that means my graph is concave up, then my function has a local minimum. And if my first derivative is 0, so I had a potential max or a min, right? It was a critical value. And the second derivative is negative, my function is concave down, then f has a local maximum at c. So let's take a look at what this will look like in a graph. So at this point right here, I have a first derivative that is 0. I have a horizontal tangent. and notice my graph is concave down. So that point has to be a maximum, while down here, I have a horizontal tangent, but my graph is concave up. That means this point is a local minimum.